There is a point in the universe where distance itself may stop existing, not become small, not become difficult to measure, but simply lose all meaning. A boundary so extreme that if you tried to look beyond it, reality would not just blur, it would collapse into something unrecognizable. This boundary is called the Planck Length, and tonight we are going to slowly drift toward it. Imagine shrinking, not just smaller than a grain of sand, not just smaller than a cell or even an atom, but far beyond anything your mind has ever needed to comprehend. Down past the nucleus, past quarks, past the very idea of particles, until you reach a scale where space itself may no longer behave like space. A place where distance may flicker, where time may hesitate, where the rules that govern everything you know quietly stop working. And what makes this even more unsettling is that this limit is not just theoretical curiosity. It is a wall, a fundamental edge built into the fabric of reality itself. If you've ever explored with us before here on Velarin's Sleepy Space Mysteries, you might remember our journey into black holes, where gravity stretches time and space to their extremes. But the Planck length takes us even deeper than that, beyond where even black holes can fully explain what is happening. Because here, we are no longer just bending reality. We are questioning whether it exists in the way we think at all. And as we gently move closer to this boundary, a series of quiet questions begin to emerge. Is space truly continuous? Or is it made of tiny, indivisible pieces? Is time flowing smoothly or ticking in invisible steps? And perhaps the most unsettling question of all, what happens if we try to go smaller than the smallest possible thing? So tonight, as you relax and let your thoughts drift, we will slowly descend through the layers of reality, from the familiar into the invisible, and finally, toward the edge where understanding begins to fade. If you enjoy these slow journeys into the quiet mysteries of the universe, consider subscribing, leaving a like, and turning on the bell so you don't miss future explorations. And if you'd like to go even deeper, you can join as a member to support the channel. And before we begin our descent, tell me softly in the comments, where in the world are you listening from tonight? As we begin this descent, nothing changes at first. The world still feels familiar, stable, continuous. You are still at the scale your senses understand, where objects have clear edges, where distances behave predictably, where space feels like an endless smooth stage stretching in all directions. But this sense of smoothness is only an illusion of scale, because the deeper we go, the more that illusion begins to quietly dissolve. Let's start with something simple. Your own body. You exist at roughly 1 to 2 meters in size, a scale perfectly tuned for human perception. Your eyes can resolve details down to about the width of a human hair, perhaps 1/10 of a millimeter if you focus carefully. Below that, the world begins to fade into blur, not because it disappears, but because your biology reaches its limit. Yet even within that invisible blur, entire worlds exist, layered beneath your awareness. If we shrink just a little further, we enter the microscopic realm. Here, a single drop of water becomes an ocean filled with motion. Tiny organisms drift, collide, divide, and live out entire lifetimes in what, to you, would feel like a single quiet moment. This was once an invisible universe, completely unknown, until early microscopes revealed that reality was not as simple as it seemed. And that discovery planted a quiet but powerful idea. If there is structure hidden below what we can see, then there may always be something deeper. So we continue. Now we pass into the scale of cells, then into molecules, where chemistry unfolds like a silent choreography. Structures assemble and disassemble with precision, guided by forces you cannot see but that shape everything around you. Still, even here, space feels continuous. Distances still behave normally. Objects still exist in recognizable forms. But this stability will not last much longer. As we move further down, we arrive at atoms. These are the building blocks of everything you know, yet they are mostly empty. If an atom were expanded to the size of a stadium, its nucleus would be no larger than a small grain at the center, with electrons existing as diffuse clouds far beyond it. Already, the idea of solid matter begins to weaken. What feels solid to you is mostly space, structured by invisible rules. And yet, even the atom is not the end. Inside the nucleus, we find protons and neutrons tightly bound together. And within them, something even smaller, quarks. These are not objects in the way you might imagine. They do not sit neatly in place. They do not have clear edges. Instead, they exist as shifting probabilities, flickering presences described not by position, but by likelihood. At this level, reality is no longer composed of tiny solid pieces. It becomes something softer, more uncertain, more fluid. And this is where the first cracks begin to appear. Because as we try to go smaller, something strange happens. Not a technological limitation, but a fundamental one. To observe something extremely small, you must use something even smaller or more energetic to probe it. This is how microscopes work, how particle accelerators work, how all observation works. But here, the rules begin to turn against us. To see something smaller, you need higher energy. And higher energy does not simply observe. It disturbs. Imagine trying to examine a delicate surface by throwing increasingly powerful objects at it. At some point, you are no longer observing the surface, you are destroying it. And this is not just an analogy. At the smallest scales, this becomes reality. The act of measuring begins to reshape what is being measured. This is where the uncertainty principle quietly emerges. It tells us that certain properties, like position and motion, cannot both be known precisely at the same time. The more clearly you try to define one, the more the other dissolves into uncertainty. And this is not due to imperfect tools. It is woven into the structure of reality itself. So as we continue shrinking, the concept of a particle having a precise location begins to fade. It becomes a cloud of possibilities, a spread of probabilities, something that is not fully there until it is observed, and even then only briefly. And yet, we keep going, because somewhere beyond this strange quantum fog lies a boundary, a limit where even these uncertain descriptions begin to fail. A place where trying to observe reality does not just disturb it, but fundamentally breaks it. We are getting closer to that edge now, a place where the act of looking becomes impossible, not because we lack the tools, but because reality itself refuses to be seen any further. And just ahead, something even stranger begins to form. As we continue descending into this increasingly unfamiliar territory, something subtle but deeply unsettling begins to emerge. Up until now, each layer of reality has revealed smaller structures hidden beneath the last, like peeling back layers of an endless cosmic fabric. But here, the pattern begins to change. It is no longer just about discovering smaller pieces. It becomes about questioning whether pieces exist at all. At the scale of quarks and fundamental particles, we already began to notice that reality behaves less like solid objects and more like shifting possibilities. But there is an even deeper consequence of this shift that is easy to overlook. If particles do not have precise positions until measured, then what does it even mean to say something exists at a specific point in space? Take a moment to imagine this. You are trying to locate something incredibly small, not by looking at it directly, but by interacting with it. You send something toward it, a probe, a particle, a wave. But the moment that probe arrives, the system changes. The particle you were trying to locate reacts. Its momentum shifts. Its position becomes uncertain. And so the more precisely you attempt to pin it down, the more you disturb its behavior. Now imagine pushing this process further. You want to measure something even smaller, so you increase the energy of your probe. Higher energy means shorter wavelengths, and shorter wavelengths allow you to resolve smaller distances. This is a fundamental relationship in physics, and it works beautifully until it doesn't. Because as the energy increases, something unexpected happens. The energy itself begins to take on a new role. It no longer acts only as a tool of observation. It begins to behave like matter. Einstein revealed that energy and mass are deeply connected. Energy can become mass, and mass can become energy. This means that when you concentrate enough energy into a small region, you are not just observing that region anymore. You are adding something to it. You are changing its very structure. And at extreme levels, this transformation becomes impossible to ignore. Imagine focusing an enormous amount of energy into a space so small that it begins to curve the fabric of reality itself. According to our understanding of gravity, mass and energy bend space and time. The more concentrated they are, the stronger this curvature becomes. And if enough energy is packed into a small enough region, that curvature becomes so intense that it forms something extraordinary. A black hole. This is the turning point, because now, the act of observing something extremely small does not just disturb it, traps it. If you try to probe distances that are too small, the energy required to do so becomes so great that it collapses into a black hole. And once that happens, nothing, not even light, can escape. The very thing you are trying to observe becomes hidden behind a horizon you cannot see through. In other words, the deeper you try to look, the more reality hides from you. This creates a paradox. To observe smaller distances, you need more energy. But more energy creates stronger gravitational effects. And eventually, those effects prevent you from observing anything at all. There is a point where these two requirements collide, where the tools of observation become the barrier itself. And that point is not arbitrary. It is a specific scale, a precise boundary where quantum mechanics and gravity meet and refuse to cooperate. This is where we begin to approach the Planck length. At this scale, something remarkable happens. The wavelength of your probing energy becomes comparable to the size of a black hole formed by that same energy. The act of measurement and the act of collapse become indistinguishable. You cannot separate observation from destruction. You cannot look without fundamentally altering the structure you are trying to understand. And so, nature imposes a limit, not a technological one, not something we might overcome with better instruments or more advanced theories, but a fundamental boundary built into the universe itself. A line that says, quietly but firmly, no further. Beyond this point, the idea of distance may no longer make sense, because distance requires a stable geometry, a consistent structure of space. But if every attempt to measure that structure creates chaos, then the structure itself cannot be defined. And so we arrive at a strange realization. The Planck length is not just the smallest measurable distance. It may be the smallest meaningful distance. Below it, space may not behave like space. Time may not behave like time. The concepts we rely on to describe reality begin to dissolve, not gradually but completely. And yet, we still don't fully understand what replaces them. Because standing at this boundary, we are faced with a deeper question. If reality has a smallest scale, what is it made of? Is space continuous, stretching infinitely with no smallest unit? Or is it built from something discrete, something like tiny indivisible fragments? And if it is discrete, what does that mean for motion, for time, for existence itself? These questions do not have simple answers, but they guide us toward the next stage of our journey. Because just beyond this boundary lies a realm where space may ripple, fluctuate, and transform into something far stranger than we have ever imagined. Now we stand at the edge of something deeply unfamiliar. Behind us lies the world we can still describe, even if imperfectly: atoms, particles, quantum uncertainty. But ahead lies a region where even those ideas begin to lose their meaning. Because once we accept that there is a smallest meaningful length, a quiet but profound shift begins to unfold. It forces us to reconsider not just what things are made of, but what space itself truly is. For most of human history, space has been treated as something smooth and continuous. You can always divide a distance into smaller parts. Take any 2 points, and there will always be another point in between. This idea feels natural, almost obvious. It is built into the mathematics we use, into the way we imagine motion, into the way we understand the universe. But the existence of the Planck length gently challenges this assumption. If there is a smallest possible unit of distance, then space cannot be infinitely divisible. It must have a kind of granularity, a hidden structure beneath its smooth appearance. Not something you can see directly, but something that defines the limits of what can exist. And this raises a strange and almost unsettling possibility that space might be more like a fabric woven from tiny threads, or even more radically, like a grid made of invisible points. But this is not a simple grid, not like squares on a screen or pixels on a display, because such structures would introduce preferred directions, breaking the symmetry we observe in nature. Instead, if space is discrete, it must be arranged in a far more subtle way. A network without obvious patterns. A structure that appears smooth from a distance, but reveals complexity only when examined at its deepest level. Now imagine what this means for motion. In a continuous space, movement is smooth. An object passes through every point along its path. It glides from one position to another without interruption. But if space is made of tiny indivisible units, then this smooth motion becomes difficult to define. There are no in-between points smaller than the smallest unit. So how does something move from one place to another? Does it jump? Does it disappear from one location and reappear in another? Or does it exist in multiple places at once, its position spread out across this hidden structure until something forces it to settle? Quantum mechanics offers a hint here. We already know that particles do not behave like tiny solid objects following precise paths. They exist as probability distributions, as waves of possibility. So perhaps motion at the smallest scale is not about traveling through space in the way we imagine, but about shifting probabilities, about transitions between states rather than movement through a continuous path. This idea becomes even more intriguing when we consider time. If space has a smallest unit, then time may also have one. A smallest possible interval, below which the concept of before and after no longer applies. This would mean that time does not flow smoothly, but advances in tiny steps, like frames in a film. Each moment distinct, each transition discrete. Yet because these steps are unimaginably small, far beyond anything we can perceive, time appears continuous to us. But if both space and time are discrete, then the universe at its deepest level may not be analog but digital. Not in the sense of computers and code, but in the sense that it is built from fundamental units that cannot be divided further. And everything we experience, motion, change, continuity, emerges from the interaction of these units. And still, this is only one possibility. There is another path, one that suggests space might remain continuous, but that something else imposes the limit. That the Planck length is not a pixel size of space, but a boundary of interaction. A scale below which our current concepts simply fail, even if space itself continues in some unknown form. This is where different theories begin to diverge. Some propose that space is indeed quantized, made of discrete building blocks that define areas and volumes. Others suggest that the fundamental entities are not points, but tiny vibrating structures, extended objects that cannot probe smaller distances because they themselves have size. And still others propose that space and time are not fundamental at all, but emerge from something deeper, something we do not yet fully understand. What they all agree on, however, is this. At the Planck scale, reality changes character, not just in degree but in kind. The familiar concepts of distance, position, motion begin to dissolve. And in their place, something more abstract, more fluid, more difficult to grasp begins to take shape. A realm where geometry itself may fluctuate, where connections between points may shift, where the structure of space is not fixed, but alive with possibility. And this leads us to an even more fascinating idea. What if space is not a passive stage on which events unfold, but an active participant in those events? What if it bends, shifts, and responds at the smallest scales, not smoothly, but in sudden, unpredictable ways? Because as we move closer to the Planck length, another concept begins to emerge. One that suggests space is not calm and empty at all, but restless, dynamic, almost turbulent. A kind of microscopic storm, foam. And within that foam, something extraordinary may be happening. As we move closer to this boundary, the idea of space as something calm and empty begins to fade completely. What once felt like a quiet, stable backdrop now starts to feel alive, unstable, almost restless. And this is where one of the most haunting ideas in modern physics begins to take shape. The idea that at the smallest scales, space is not smooth at all, but instead resembles something more chaotic. Something constantly shifting, forming, dissolving. Something often described as quantum foam. To understand this, imagine looking at the surface of a vast ocean from very high above. From that distance, it appears perfectly smooth. A calm, uninterrupted sheet stretching to the horizon. But as you slowly descend, getting closer and closer, that smoothness begins to break. Waves appear, ripples form, patterns emerge. And if you go close enough, you no longer see a surface at all, but a chaotic dance of water rising and falling, colliding and breaking, never still. Now imagine that space itself behaves in a similar way. At the scale of planets and stars, space appears smooth and continuous. Even at the level of atoms, it still behaves predictably. But as we approach the Planck length, this apparent smoothness may dissolve into something far more turbulent. Not waves of water, but fluctuations of geometry itself. Tiny distortions in space and time, constantly forming and vanishing. And these are not gentle fluctuations. At this scale, the uncertainty principle allows for brief, intense bursts of energy to appear and disappear. Normally, these fluctuations are subtle, their effects only noticeable in delicate experiments. But at extremely small scales, the rules allow for something much more dramatic. Energy can spike to enormous levels, as long as it vanishes quickly enough. And when that happens, something extraordinary may occur. Because as we've already seen, concentrated energy bends space. And enough energy can create a black hole. So at the Planck scale, where these fluctuations are incredibly intense, it is possible that tiny black holes could form spontaneously. Not the massive ones formed by collapsing stars, but microscopic, fleeting versions that exist for only the briefest moment. They would appear and vanish almost instantly, too fast to observe directly, too small to detect with any instrument, but their presence would mean that space itself is not stable. It would be constantly punctured by these tiny gravitational collapses, forming and evaporating in an endless, chaotic process. This is the essence of quantum foam, a picture of reality where space is not a smooth fabric, but a seething, dynamic structure. A place where geometry itself fluctuates, where distances are not fixed, where the very connections between points can change from moment to moment. And it doesn't stop there. Some theories suggest that along with these tiny black holes, equally strange structures could appear. Wormholes, brief tunnels connecting distant points in space, forming and collapsing in an instant. Imagine two regions of space that are normally far apart suddenly becoming connected, if only for a fraction of a moment, before the connection disappears again. If this is true, then the structure of space at the smallest scale is not just unstable, it is constantly rearranging itself. Distances may fluctuate, connections may shift. The concept of here and there may lose its clear meaning. Because if space can momentarily connect distant points, then distance is no longer a fixed property. It becomes something fluid, something that depends on the underlying state of this quantum foam. And this leads to a profound realization. At the Planck scale, geometry itself may not be well defined. The idea of measuring a distance assumes that space has a stable structure. But if that structure is constantly fluctuating, then any measurement becomes uncertain, not just because of our tools, but because the thing being measured does not have a fixed value. Distance becomes fuzzy. Time becomes uncertain. Even causality, the idea that one event leads to another, may become less clear as the structure connecting events shifts beneath them. This is where our usual understanding begins to break completely, because all of physics, all of our descriptions of reality, rely on the assumption that space and time form a stable stage. But here, the stage itself is changing. It is no longer a passive background. It is an active, dynamic participant. And so we are left with a strange and almost poetic image. A universe where, at its deepest level, everything is in motion, not just matter and energy, but space and time themselves. A place where reality is not built on solid ground, but on something more like a constantly shifting sea. And yet, even this picture may not be complete, because describing this foam is only the beginning, tells us what might be happening, but not why. It does not explain what rules govern this chaos, or what deeper structure might give rise to it. To answer those questions, physicists have begun to explore entirely new frameworks, new ways of thinking about reality that go beyond particles and fields, beyond smooth space and continuous time. And in the next stage of our journey, we will begin to explore those ideas. The attempts to understand what lies beneath the foam, what truly defines the Planck scale, and whether reality at its deepest level is something entirely different from anything we have ever imagined. Now, as we reach the deepest point of this descent, something becomes quietly clear. Everything we have explored so far, the atoms, the particles, the uncertainty, the limits of measurement, the restless foam of spacetime, it all leads to a single, unavoidable realization. The universe at its smallest scale is not just unfamiliar, it may be fundamentally unknowable in the way we are used to knowing things. And yet, instead of stopping here, physics does something remarkable. Keeps going. Because even though we cannot directly observe what happens at the Planck length, we can still try to understand it. Not by looking, but by thinking, by building models, by asking what kind of deeper structure could give rise to everything we have seen so far. And this is where some of the most ambitious ideas in science begin to emerge. One of these ideas suggests that what we perceive as particles are not truly point-like at all. Instead, they may be tiny, vibrating strands of energy, not dots but strings, infinitely small from our perspective, yet still extended objects with length but no thickness. And the way these strings vibrate determines what kind of particle they appear to be. A single fundamental object, giving rise to many different forms. In this view, an electron is not a tiny sphere. It is a pattern of vibration, a specific mode of oscillation, and a quark is simply another pattern, another note played on the same underlying string. Just as a musical instrument can produce different sounds depending on how it vibrates, the universe itself may produce different particles through different vibrational states. And here is where it connects back to our journey. These strings are thought to exist at the Planck scale, which means that from our perspective they appear as points, not because they are truly point-like, but because we cannot resolve their structure. We are simply too far away, too limited by the very boundary we have been approaching. And so what looks like a particle may actually be something far richer, hidden just beyond our ability to see. But this idea comes with a strange consequence. For these strings to behave consistently, the universe may require more dimensions than the ones we experience. Not just the familiar 3 dimensions of space and 1 of time, but additional dimensions, curled up so tightly that they exist only at the smallest scales. Invisible to us, yet shaping the behavior of everything. Imagine that at every point in space, there are hidden directions folded in on themselves, too small to notice. Directions you cannot move through, not because they do not exist, but because they are compressed beyond perception. And the shape of these hidden dimensions could determine the properties of particles, the strengths of forces, even the structure of reality itself. It is a beautiful idea, but it is not the only one. Another approach takes a very different path. Instead of replacing particles with strings, it asks a more radical question. What if space itself is the thing that must be quantized? What if the fabric of reality is not smooth, but made of tiny discrete units, woven together in a vast dynamic network? In this picture, space is not a stage. It is a structure, a web of connections, a network of relationships, and what we perceive as distance, as area, as volume, emerges from how these connections are arranged. At the smallest scale, there is no continuous geometry, only a kind of underlying scaffolding, constantly evolving, constantly reshaping itself. And from this scaffolding, space appears. Time appears. Reality as we experience it emerges. Both of these ideas, vibrating strings and discrete space, are attempts to answer the same question. What lies beneath the Planck length? What is the true nature of the boundary we cannot cross? And so far, we do not know. There is no experiment that can confirm one theory over the other. No observation that can reveal the structure directly, because the scale is simply too small. The energy required to probe it is beyond anything we can currently achieve, and perhaps beyond anything we ever will. And yet, this does not make the search meaningless, because even without direct access, these ideas help us understand the limits of our knowledge. They show us where our current theories break down. They guide us toward a deeper, more unified description of reality, even if that description remains just out of reach. And perhaps that is the most fascinating part of all, that the universe contains a boundary, not just of size, but of understanding. A place where our concepts begin to fail, where intuition no longer applies, where even the idea of what is happening becomes difficult to define. And still, we are drawn to it, because standing at this edge, we begin to sense something profound. That reality is not as simple as it appears. That beneath the smooth surface of space and time lies something deeper, more complex, more mysterious than anything we can directly observe. And as we gently leave this part of our journey behind, we carry that mystery with us. A quiet awareness that there is a limit, and that beyond it something waits. Something we are only just beginning to imagine. If you're still here with me, slowly drifting through these layers of reality, let me know by softly typing the number 1 in the comments. And when you're ready, we'll continue even deeper into the place where physics itself begins to break, and reality becomes something else entirely. Now we move beyond the boundary we could only approach before, into a region where our most trusted theories begin to quietly unravel. Up until now, we have followed a path that still held some sense of structure. Even when reality became uncertain, even when particles dissolved into probabilities, there were still rules guiding that uncertainty. But here, something deeper begins to fracture. Because at the Planck scale, 2 of the greatest pillars of physics meet, and they do not agree. On one side, there is quantum mechanics, a theory that governs the smallest scales, describing particles as waves of probability, allowing fluctuations, uncertainty, and constant motion even in what we would call empty space. It is a theory that has been tested with incredible precision, predicting outcomes with astonishing accuracy. It tells us that even a perfect vacuum is never truly empty, but filled with fleeting activity, particles appearing and disappearing in a quiet, endless dance. On the other side, there is gravity, not as a force in the traditional sense, but as a curvature of spacetime itself. According to our best understanding, mass and energy bend the fabric of reality, shaping how objects move, how time flows, how distances behave. This picture, described by general relativity, works beautifully on large scales, from planets to galaxies to the expansion of the universe itself. Individually, these 2 frameworks are among the most successful ideas humanity has ever created. But together, they create a problem. Because quantum mechanics assumes that spacetime is a fixed stage, a stable background where probabilities unfold. It does not question the structure of space itself. It simply operates within it. Meanwhile, general relativity tells us that spacetime is not fixed at all. It is dynamic, flexible, shaped by energy and mass, constantly responding to what exists within it. And when we bring these two ideas together at extremely small scales, the contradictions become impossible to ignore. Imagine trying to describe a region of space that is both fluctuating wildly due to quantum effects, and at the same time being bent and distorted by gravity. Quantum mechanics would say that energy is constantly appearing and disappearing in that region. General relativity would say that energy curves spacetime. So if energy is fluctuating, then spacetime must also be fluctuating. But how do you describe a geometry that is constantly changing? What does distance mean if the structure defining that distance is unstable? What does before and after mean if time itself is part of that fluctuating structure? This is where our equations begin to fail. When physicists try to calculate what happens when gravity is treated using quantum rules, the results do not behave nicely. Instead of producing meaningful answers, the equations explode into infinities. Values grow without limit, losing all physical meaning. It is not just a small error or an approximation problem. It is a signal that something deeper is missing, that the frameworks we are using are not compatible in this regime. And this is why the Planck length is so important. It marks the scale where both quantum effects and gravitational effects become equally strong. A place where neither theory can be ignored, but neither can fully describe what is happening. It is the point where our understanding reaches its edge, where the map we have drawn of reality simply stops. But rather than seeing this as a dead end, physicists see it as a doorway. Because if two successful theories fail when combined, it suggests that there is a deeper theory beneath them. A more fundamental description of reality that includes both as approximations. Something that works not just at large scales or small scales, but at all scales. This search has a name: quantum gravity. It is one of the greatest unsolved problems in science. A quest to unify the behavior of the very large and the very small into a single coherent framework. A theory that can describe what happens at the Planck scale without breaking down. And the stakes are enormous, because such a theory would not only explain the Planck length. It would tell us what happens inside black holes, where gravity becomes extreme. It would describe the earliest moments of the universe, when everything was compressed into a region smaller than this fundamental limit. It would reveal whether space is truly continuous or built from discrete pieces. It might even change our understanding of time itself. But finding this theory is not easy. For decades, physicists have explored different paths, each offering a glimpse of what might lie beneath the surface. Some approaches try to extend quantum mechanics to include gravity. Others attempt to rebuild spacetime from more fundamental ingredients. Each one brings new insights and new questions. And as we continue our journey, we will begin to explore these ideas. Not as final answers, but as attempts, as ways of reaching into the unknown and trying to make sense of it. Because beyond the Planck length, we are no longer just asking what the universe is made of. We are asking what reality is. If quantum gravity is the doorway, then the question becomes what lies on the other side. For decades, physicists have been trying to answer this, not with direct observation, but with imagination guided by mathematics. And one of the most compelling ideas to emerge from this search begins with a simple but radical shift in perspective. Instead of thinking of particles as tiny points, it asks us to imagine them as something extended, something that has length even if that length is unimaginably small. This idea is known as string theory. At first, it may seem like a small change, replacing points with tiny strings. But this change carries enormous consequences, because point-like particles, when pushed to extreme energies, tend to create the infinities that break our equations. They concentrate everything into a single location, with no structure to soften the interaction. But a string, even an incredibly small one, spreads that interaction out. It introduces a kind of natural limit, a smoothing effect that prevents those infinities from forming in the same way. And this is where something remarkable happens. When physicists explored how these tiny strings would behave, they discovered that one of the possible vibration patterns naturally corresponds to something very familiar: gravity. Not added in by hand, not forced into the theory, but emerging on its own. As if gravity were not a separate ingredient, but an inevitable consequence of the deeper structure. This was unexpected, because for so long gravity had resisted attempts to be described in quantum terms. And yet here, in this framework of vibrating strings, it appeared effortlessly. A quiet hint that perhaps this approach was touching something real. But as beautiful as this idea is, it comes with a cost. For the mathematics to work consistently, the universe must have more dimensions than we experience. Not just 3 dimensions of space, but additional ones hidden from view. These extra dimensions are not large like the ones we move through. Instead, they are thought to be tightly curled, folded into shapes so small that they exist only at the Planck scale. To picture this, imagine walking along a thin wire. From a distance, the wire looks one-dimensional. You can move forward or backward along it. But if you were small enough, you would notice that the wire has a surface. You could move around it as well in a direction that was invisible from afar. This hidden direction is always there, just too small to notice. String theory suggests that reality may be filled with such hidden directions. At every point in space, additional dimensions may be curled up, shaping how strings vibrate. And because the vibration patterns determine the properties of particles, the geometry of these hidden dimensions could define the entire structure of the universe. The masses of particles, the strengths of forces, even the existence of different types of matter, all emerging from the shape of something we cannot see. It is a deeply elegant idea, but it also introduces a new mystery. There may not be just one way for these extra dimensions to be arranged. There could be countless possible shapes, each leading to a different version of physics, a different universe with different laws. And if that is true, then why does our universe have the specific properties we observe? This question remains unanswered. And so, while string theory offers a powerful framework, it does not yet provide a complete explanation. It opens the door, but does not fully reveal what lies beyond. At the same time, another approach takes a very different direction. Instead of changing what particles are, it changes what space is. This idea is known as loop quantum gravity. Rather than treating spacetime as a smooth continuum, it suggests that space itself is made of discrete units. Not particles within space, but space itself broken into tiny building blocks. These building blocks are not arranged in a simple grid, but in a complex network, a web of connections that define how space is structured. In this view, there is no background space in which things exist. The network is the space. Distances, areas, volumes, all emerge from the relationships between these connections. And because these connections are quantized, they can only take certain values. This means there is a smallest possible unit of area, a smallest possible unit of volume, all tied to the Planck scale. And this has a fascinating implication. If space is made of discrete units, then the smooth geometry we experience is an illusion of scale. Just as a fabric appears continuous from a distance but reveals individual threads up close, spacetime may only appear smooth because we are observing it from far above its fundamental structure. But at the Planck scale, those threads become visible, and the geometry becomes granular. This approach does not require extra dimensions. It does not replace particles with strings. Instead, it focuses directly on the structure of spacetime itself, attempting to rebuild it from the ground up using quantum principles. And yet, like string theory, it remains incomplete. It offers insights, predictions, and mathematical consistency, but no direct experimental confirmation. Because once again, the Planck scale remains beyond our reach. So we are left with multiple visions of what reality might be at its deepest level. A universe of vibrating strings in hidden dimensions. A universe woven from discrete loops of spacetime. Perhaps something else entirely, still undiscovered. And as we stand between these possibilities, one thing becomes clear. We are not just exploring smaller distances. We are exploring the limits of understanding itself. As these different visions of reality begin to take shape, something subtle but deeply important emerges. Despite their differences, despite the different mathematics, the different assumptions, the different directions, they all point toward the same quiet conclusion. That at the Planck scale, reality is not built the way we intuitively imagine. Not from solid objects moving through empty space, but from relationships, structures, and patterns that give rise to space itself. And this shift in perspective opens the door to an even more profound idea. What if space and time are not fundamental at all? What if they are not the base layer of reality, but something that emerges, like temperature emerges from the motion of molecules, or like a wave emerges from the movement of water? This idea is known as emergent spacetime, and at first it feels almost impossible to grasp, because everything you have ever experienced exists within space and time. Every movement, every thought, every moment of awareness depends on them. So to suggest that they are not fundamental is to suggest that the stage on which reality unfolds is itself a kind of illusion. Not a false illusion, but a higher level description of something deeper. To understand this, imagine looking at a crowd from far above. From a distance, the crowd appears as a flowing pattern, almost like a liquid. You can describe it in terms of waves, densities, motion. But up close, there is no fluid. There are only individuals, each moving according to their own interactions. The smooth flow is not fundamental. It emerges from the collective behavior. Now apply this idea to spacetime. What if the smooth geometry we experience is like that flowing crowd, an emergent pattern arising from countless microscopic interactions? And at the Planck scale, those interactions are no longer hidden. The underlying structure becomes visible, and the illusion of smoothness begins to break. In such a picture, space is not something that exists first with objects inside it. Instead, the relationships between fundamental elements give rise to what we perceive as space. Distance becomes a measure of how those elements are connected. Time becomes a measure of how those connections change. And this leads to a strange but powerful realization. If space and time emerge from something deeper, then asking what exists inside space may not make sense. Because space itself is not the container. It is the result. This idea connects to several modern approaches. Some suggest that reality is fundamentally made of information. Not particles, not fields, but bits of information that encode relationships. In this view, the universe is not built from matter, but from the structure of information itself. And spacetime emerges as a way of organizing that information. Others propose that gravity is not a fundamental force at all, but an emergent phenomenon. Something that arises from the statistical behavior of microscopic degrees of freedom, much like pressure arises from the motion of particles in a gas. In this picture, what we experience as gravity is not a basic interaction, but a large-scale effect of deeper processes. These ideas are still developing, still being explored, still far from complete. But they all share a common theme. They suggest that the Planck length is not just a boundary of measurement, but a boundary of description. Below this scale, the language we use, space, time, distance, motion, may no longer apply. Not because reality disappears, but because it is no longer structured in a way that those concepts can describe. And this brings us back to something we touched on earlier. The idea that at the Planck scale, geometry itself becomes unstable. But now we can see this in a new light. Perhaps it is not that geometry fluctuates wildly in the way we imagine, but that geometry is not the correct concept at all. That what appears as fluctuating spacetime is actually the surface of something deeper, something that does not resemble space in any familiar sense. And this leads to one of the most fascinating possibilities. That reality at its deepest level may not be spatial, not located in a place, not extended in dimensions, but instead existing as a network of relationships from which space itself emerges as a kind of projection. If this is true, then the Planck length is not the smallest piece of space. It is the scale at which space itself dissolves. And beyond it, there may be no distance to measure, no direction to move, no geometry to define, only structure, in a form we are still struggling to understand. And yet, Even as these ideas stretch the limits of imagination, they remain grounded in a simple motivation: to reconcile what we already know, to build a consistent picture that includes both quantum mechanics and gravity, to explain why the universe behaves the way it does, from the largest galaxies to the smallest conceivable scale. But as we continue, another question begins to quietly form. If space and time emerge from something deeper, then what does that mean for the beginning of the universe itself? Because there was a moment when everything was compressed to scales near the Planck length. A moment where these deeper rules were not hidden, but dominant. And to understand that moment, we must turn our attention to the very beginning, to the earliest phase of the universe, where space, time, and everything we know may not yet have existed in their familiar form. As we gently shift our focus toward the beginning of everything, the mystery deepens in a way that feels almost paradoxical. Because the Planck length is not just a boundary in space. It is also tied to a boundary in time. A moment so early, so compressed, that our usual understanding of before and after begins to lose its meaning. This moment is often called the Planck epoch, the earliest phase of the universe, where everything we have discussed was not hidden beneath layers of scale, but fully exposed. To imagine this, we must let go of the idea of a vast universe filled with stars and galaxies. Instead, picture everything, every particle, every field, every possible structure, compressed into a region so small that it approaches the Planck length itself. Not just dense, but fundamentally beyond what our current physics can describe. At this stage, the universe is not just hot. It is unimaginably energetic. Temperatures so extreme that the distinction between different forces may not exist. Gravity, electromagnetism, the strong and weak nuclear forces, all may merge into a single unified interaction. A state where the familiar divisions of physics dissolve, replaced by something simpler, yet far more difficult to understand. And here something extraordinary happens. The very concepts of space and time begin to blur. Because if spacetime itself is subject to quantum fluctuations, as we explored earlier, then at this earliest moment, those fluctuations would not be small disturbances. They would dominate everything. Space would not be a stable arena. Time would not flow smoothly. Instead, both would exist in a kind of undefined state, a shifting structure where geometry has not yet settled into the form we recognize. This leads to a profound question. What does it mean to say that the universe began at this moment? In our everyday experience, beginnings are tied to time. Something happens after something else. But if time itself is not yet well defined, then the idea of a beginning becomes unclear. It is like asking what lies north of the North Pole. The question feels meaningful, but it may not have an answer within the framework we are using. Some physicists have proposed that time itself emerges from this early state, that before a certain point, there is no meaningful distinction between past and future. Instead, there is only a kind of timeless configuration, a quantum state from which time gradually unfolds as the universe expands and cools. In this view, the Big Bang is not a moment in time, but the point where time begins to make sense. And this changes how we think about the origin of everything. Because if time did not exist in the way we understand it before the Planck epoch, then asking what happened before the universe may not be a valid question. There may be no before at all, at least not in the conventional sense. But this is only one possibility. Another idea suggests that the universe did not begin from nothing, but from a previous state. That instead of a singular beginning, there was a transition, a moment where a prior phase of the universe reached an extreme density, approaching the Planck scale, and then underwent a transformation, a kind of bounce. In this scenario, the universe could be cyclical, expanding, contracting, reaching a limit, and then expanding again. The Planck scale would act as a kind of barrier, preventing infinite compression, replacing the classical idea of a singularity with something finite, something governed by quantum effects. This idea is deeply connected to the notion that quantum gravity may resolve the infinities predicted by classical theories. Just as quantum mechanics prevents electrons from collapsing into atomic nuclei, perhaps quantum gravity prevents the universe from collapsing into a point of infinite density. And if that is true, then the Planck length is not just a limit of measurement. It is a protective boundary, a scale that prevents reality from breaking completely. But even here, uncertainty remains. We do not yet have a complete theory of quantum gravity. We cannot fully describe what happens at the Planck epoch. We can only build models, explore possibilities, and search for indirect clues in the structure of the universe we observe today. And yet, despite this uncertainty, something remarkable stands out. All of these ideas, whether time emerges, whether the universe bounces, whether spacetime itself is replaced by something deeper, point to the same conclusion: that the Planck scale is not just a small detail in physics. It is the foundation, the place where the rules of reality are written, or perhaps rewritten. And as we reflect on this, another quiet question begins to form. If the universe began or transformed or emerged at this scale, then everything we see today, galaxies, stars, planets, even ourselves, traces back to a state where space and time were not yet what they are now. Which means that the reality we experience is not fundamental. It is the result of a transformation, a gradual unfolding from something deeper, something simpler, something we are only beginning to glimpse. And in the next part of our journey, we will explore what that means for the nature of reality itself. Because if space, time, and even existence emerge from the Planck scale, then the question is no longer just how the universe works, but why it appears the way it does at all. As we arrive at the end of this part of our journey, everything we have explored begins to gently converge into a single, quiet realization. Not a conclusion, but a shift in perspective. Because what the Planck length ultimately reveals is not just a limit of size, but a limit of how we understand reality itself. Up until now, we have followed the idea that the universe is built from smaller and smaller pieces. Atoms made of particles, particles perhaps made of strings or quantum structures, all layered beneath one another like an infinite descent. But as we reach the Planck scale, that idea begins to dissolve. There may not be a smallest piece in the way we imagine. Instead, there may be a transition, a point where the very concept of pieces no longer applies. Because below this scale, the language we rely on, distance, location, movement, may simply stop working. And this leads to something both unsettling and strangely beautiful. That reality at its deepest level may not be something we can picture. Not a tiny world hidden beneath our own, but something entirely different in nature. Something that does not exist within space, but gives rise to space. Something that does not move through time, but allows time to emerge. And if that is true, then everything we experience, the vastness of the cosmos, the passage of time, even the sense of being here now, is part of a higher level description. A kind of projection emerging from a deeper, more abstract foundation. This does not make reality less real. In a way, it makes it more profound, because it suggests that what we see is not the base layer, but the surface of something far more intricate. A structure that we are only beginning to sense, like shadows hinting at a hidden form. And yet, despite all of this, we are not completely disconnected from that deeper level. Because the Planck length leaves traces. It defines the limits of black holes. It shapes the earliest moments of the universe. It appears in the constants that govern everything we observe. It is woven quietly into the equations that describe reality, even if we cannot directly reach it. It is like a boundary we cannot cross, but can still feel. And perhaps that is why it continues to draw attention. Not because we expect to fully understand it anytime soon, but because it marks the edge of something important. A place where our current knowledge ends, and something new must begin. Throughout history, moments like this have always led to transformation. When classical physics could no longer explain atomic behavior, quantum mechanics emerged. When Newton's laws could not describe gravity at large scales, relativity reshaped our understanding. And now, once again, we stand at a boundary. The Planck scale is not just a mystery. It is an invitation to rethink what space is, what time is, what existence itself might be. And yet, even as we explore these ideas, there is a quiet acceptance that some aspects of this boundary may remain beyond us. Not because we lack intelligence or creativity, but because the universe itself may place limits on what can be known. And that thought, rather than being discouraging, carries a certain calm, because it reminds us that the universe is not obligated to be simple. It is not required to fit neatly into human intuition. It can be vast, complex, and mysterious, and still be beautiful. And so, as we slowly transition toward the final part of our journey, we carry with us a different kind of understanding. Not a clear answer, but a deeper question. If reality is not built from what we can see, if space and time are not fundamental, if the universe emerges from something beyond our current language, then what does it truly mean to exist within it? What does it mean to be part of a universe whose deepest layer may never fully reveal itself? These are not questions that demand immediate answers. They are questions meant to linger, to settle gently in the background of thought, like distant stars, always present, quietly guiding our sense of wonder. If you're still here, still drifting through these ideas with me, let me know by softly typing the number 2 in the comments. And when you're ready, we'll move into the final part of our journey, where everything we've explored begins to slow, and we reflect on what it all might mean. As we enter the final stage of this journey, everything begins to slow, not because the mystery has ended, but because we are no longer moving deeper into smaller scales. Instead, we are gently stepping back, carrying with us everything we have discovered, and allowing it to settle into a quieter understanding. Because what the Planck length ultimately gives us is not just a boundary of physics, but a new way of seeing the universe itself. For a long time, it was natural to imagine reality as something built from the bottom up. Tiny pieces assembling into larger structures, forming atoms, then molecules, then stars, then galaxies. A kind of cosmic construction, layer upon layer, each level resting on something smaller beneath it. But now, after everything we've explored, that picture begins to soften. Because at the deepest level, there may not be a foundation in the way we expect. There may not be a smallest thing. Instead, there may be a transition, a place where the idea of things dissolves into something more abstract, where structure replaces substance, where relationships matter more than objects, and where space itself is no longer the stage, but something that emerges from deeper patterns. And this changes how we think about existence, because if space is not fundamental, then being somewhere is not a basic property of reality. It is something that arises at larger scales, like a kind of approximation. At the smallest level, there may be no clear sense of location, no fixed positions, only connections, interactions, and transformations that give rise to the appearance of place. The same may be true for time. We experience time as a steady flow, a continuous movement from past to future. But at the Planck scale, that flow may not exist in the same way. Instead, time may emerge from sequences of changes, from transitions between states. Not a river flowing, but a series of moments connected in a deeper, more subtle structure. And when we put these ideas together, something remarkable appears. A picture of the universe that is not built from objects moving through space and time, but from patterns that generate space and time themselves. It is a quiet shift, but a profound one, because it suggests that everything we experience, the vastness of the night sky, the motion of planets, the passage of days, is not the most fundamental layer of reality. It is a kind of surface, a stable pattern that emerges from something far more dynamic beneath it. And yet, this does not make our experience any less meaningful. In fact, it may make it more so, because it shows that complexity can arise from simplicity. That something as rich and structured as the universe we observe can emerge from rules that operate at scales we cannot directly access. It reminds us that what we see is only part of the story, but still a real and beautiful part. And there is something else that begins to feel different as well. The idea of limits. At first, the Planck length might seem like a restriction, a boundary we cannot cross, a place where knowledge stops. But from another perspective, it can be seen as something else entirely. A sign that the universe has structure, that it is not infinitely divisible in a simple way, but organized according to deeper principles. A kind of hidden order, because without such limits, reality might behave very differently. There might be no stability, no consistent patterns, no reliable laws. The existence of a smallest scale may be what allows everything above it to exist in a coherent way. So instead of seeing the Planck length as a wall, we can begin to see it as a foundation of a different kind. Not a physical base made of smaller pieces, but a conceptual boundary that defines how reality can behave. And as we sit with that idea, something begins to feel calmer, because the need to go further, to break through the boundary, to see what lies beyond, slowly fades. Not because the curiosity disappears, but because we begin to understand that some mysteries are not meant to be fully resolved. They are meant to be approached, explored, felt. And in that sense, the Planck length is not just a scientific concept. It is a reminder that the universe is deeper than our models, richer than our language, and more subtle than our intuition. And as we continue, we will not push further down, but instead allow ourselves to drift outward again, carrying this quiet awareness with us. Because sometimes, understanding does not come from going deeper, but from seeing everything a little differently. As we continue this gentle return from the deepest layers of reality, something begins to shift in how we hold these ideas in our mind. Earlier, we were moving downward, peeling back layer after layer, searching for the smallest possible structure. But now, instead of searching for what lies beneath, we begin to notice how everything above is quietly shaped by what we cannot see. Because even if the Planck length remains unreachable, its influence is everywhere. It defines the scale at which black holes become unstable, where their temperature rises, where they begin to evaporate almost instantly. It sets the stage for the earliest moments of the universe, when everything was compressed into a state beyond ordinary description. It appears in the constants that govern physics, quietly linking gravity, quantum mechanics, and the speed of light into a single framework. It is like a hidden rhythm, not something you hear directly, but something that shapes the entire melody. And this invites a different kind of reflection. Instead of asking what exists beyond the Planck length, we can ask, how does its existence shape the universe we experience? Because if there is a smallest meaningful scale, then everything larger than it must be built in a way that respects that limit. Every structure, every interaction, every process unfolds within a framework that cannot be divided endlessly. And this may be part of why the universe feels stable, why patterns repeat, why laws remain consistent across vast distances and times. It is as if the universe is quietly anchored not by something we can see, but by something that defines the boundaries of possibility. And yet, even with this grounding, there is still a sense of openness. Because the Planck length does not tell us exactly what lies beneath it. It does not reveal the deeper structure in full detail. It only tells us that such a structure must exist, and that it operates in a way fundamentally different from what we are used to. This leaves space for imagination. Not wild speculation, but careful, thoughtful exploration. The kind that physics has always relied on. building models, testing ideas, refining our understanding step by step. Even if we cannot reach the Planck scale directly, we can still approach it from different directions, using the clues it leaves behind. For example, by studying black holes, we can glimpse how gravity and quantum effects might interact. By observing the cosmic background radiation, we can gather hints about the earliest moments of the universe. By examining the behavior of particles at high energies, we can push our theories closer to their limits. Each of these approaches is like shining a light from a different angle, hoping to catch a reflection of something deeper. And sometimes those reflections are enough to guide us forward. But there is also a quieter realization that emerges here, that even if we never fully uncover what lies beyond the Planck length, the journey itself has value, because it changes how we see the universe. It reminds us that what appears simple may hide extraordinary complexity, that what feels continuous may be built from something discrete, that what seems fundamental may itself be an emergent pattern. And perhaps most importantly, it shows us that there are limits, not just limits of technology, but limits of description. Boundaries where our current language, our current concepts no longer apply. And instead of resisting those limits, we can learn to sit with them, to explore up to their edge, and then allow ourselves to rest there. There is something peaceful in that, because it shifts the goal from complete understanding to deeper appreciation, from trying to control the universe through explanation, to quietly observing its structure, its patterns, its mysteries. And as we hold that perspective, the Planck length begins to feel less like a barrier and more like a horizon, not something that stops us, but something that defines the edge of what can currently be seen. Beyond it, there may be more, perhaps entirely new principles, perhaps a completely different way of describing reality. But for now, that region remains softly hidden, like a distant landscape just beyond the reach of light. And that is okay, because even within what we can observe, there is already more than enough to inspire wonder. Galaxies stretching across billions of light years, black holes bending time itself, particles flickering in and out of existence, and beneath it all, a quiet boundary, shaping everything without ever revealing itself directly. And so, as we continue to slow down, to move away from the edge and back toward a wider view, we begin to carry a different kind of understanding. Not one built on certainty, but on awareness. Awareness of depth, of limits, of the quiet complexity that lies beneath even the simplest things. And in the final part of this journey, we will let that awareness settle fully into a calm reflection on what it means to exist in a universe like this. A universe with boundaries, and yet endless mystery. As we continue to drift outward from the smallest scales, something gently settles into place. Not a final answer, but a quiet acceptance of perspective. Because what the Planck length has shown us is not just that there is a limit, but that reality may be layered in a way that invites both understanding and mystery at the same time. Think for a moment about how we normally experience the world. You see objects around you solid, stable, clearly defined. A table, a wall, the ground beneath your feet. They feel real, continuous, dependable. But now, after everything we've explored, you know that beneath that apparent solidity, there is mostly empty space. Beneath that, particles that are not really particles in the classical sense. Beneath that, uncertainty. And beneath that, a boundary where even the idea of space begins to dissolve. And yet, none of this makes the table any less real. It simply reveals that reality exists on multiple levels at once. Each level valid in its own way. Each level describing the same universe, but through a different lens. At your scale, the world is solid and predictable. At smaller scales, it becomes probabilistic and fluid. And at the Planck scale, it becomes something we cannot fully describe, something that resists being placed into familiar categories. This layered nature of reality is one of the most profound insights we can take from this journey, because it reminds us that understanding does not always mean reducing everything to a single explanation. Sometimes it means recognizing that different descriptions coexist, each revealing part of a larger picture. The smooth flow of time and the discrete possibility of quantum events. The curvature of spacetime and the fluctuations beneath it. The vastness of galaxies and the tiny limits that shape them. All of these are not contradictions. They are perspectives. And the Planck length sits quietly at the boundary between them. Now, as we slow even further, another thought begins to emerge. One that feels less like a scientific conclusion and more like a gentle reflection. If the deepest layer of reality is not directly accessible, if it cannot be fully visualized, measured, or even described using our current concepts, then perhaps the universe is not meant to be completely understood in a single final sense. Not because it is beyond intelligence, but because it is richer than any one framework. And this idea carries a kind of calm, because it releases the pressure to reach a final answer. It allows us to explore, to learn, to build models and theories, while also accepting that there may always be more beyond them, that every answer opens new questions, that every boundary hints at something deeper. And in that way, the Planck length becomes more than a physical limit. It becomes a symbol, a reminder that knowledge has edges, and that those edges are not failures, but invitations. Invitations to keep wondering, to keep exploring, to remain curious, even when clarity fades. And perhaps this is where the journey becomes personal. Because when we think about existence, not just in terms of particles and space, but in terms of experience, we begin to notice something similar. We understand many things about the world, but not everything. There are moments of clarity and moments of mystery. There are patterns we can explain and others that remain just out of reach. And yet we continue, not because we expect to solve everything, but because the process itself has meaning. In the same way, physics continues to approach the Planck scale, not because it expects an easy answer, but because each step reveals something new, something that reshapes how we see the universe, even if it does not complete the picture. And so, as we gently approach the final moments of this journey, we carry with us a different kind of understanding. Not one built on certainty, but on depth, on the awareness that reality is layered, subtle, and endlessly rich, on the recognition that even the smallest scale can reshape how we see the largest, and on the quiet realization that some mysteries are not meant to be solved quickly, but experienced slowly, like this journey itself. As the journey continues to slow, there is a gentle shift from questioning to simply observing, not searching for deeper layers anymore, but allowing everything we have uncovered to settle into a quiet sense of perspective. Because what began as a descent into the smallest possible scale has gradually transformed into something else entirely. Not just an exploration of physics, but a reflection on the nature of reality itself. And in this stillness, one idea begins to feel more present than the others. That the universe does not need to be fully understood to be deeply meaningful. For so long, the pursuit of knowledge has been driven by the idea that there is an ultimate answer waiting at the end. A final layer, a smallest piece, a complete explanation that ties everything together. But the Planck length gently challenges that idea. It suggests that there may not be a final, simple foundation in the way we imagine. Instead, there may always be another layer of abstraction, another level of description, another way of seeing. Not infinite in the sense of endless pieces, but infinite in the sense of depth. And that changes how we relate to the unknown. Because instead of seeing it as something to overcome, we can begin to see it as something to coexist with. A quiet presence at the edge of understanding, not blocking us, but reminding us that there is always more beyond what we currently see. If you imagine standing at the shore of a vast ocean at night, you can see only a small distance into the water. Beyond that, everything fades into darkness. But that darkness is not empty. It is simply beyond your current reach. And yet, knowing it is there adds to the experience. It deepens it. It gives the ocean a sense of scale, of mystery, of quiet infinity. The Planck length is something like that horizon. It marks the point where our view fades, and not because there is nothing beyond it, but because what lies beyond belongs to a different kind of understanding. And perhaps, in a way, this is what makes the universe feel so expansive, not just in size but in meaning, because even the smallest scale carries mystery. Even the deepest level holds questions. And no matter how far we go, there is always something just beyond the edge. But rather than creating discomfort, this can create a sense of calm, because it allows us to stop searching for a final endpoint, to stop expecting that everything must resolve into a single, complete answer, and instead to appreciate the layers as they are. The world we experience, stable and familiar. The quantum world, fluid and uncertain. The Planck scale, mysterious and undefined. Each one real in its own way. Each one part of the same universe. And somewhere within all of this is us. Observers, participants, aware of both the clarity and the mystery at the same time. And that awareness itself is something remarkable, because it means that the universe is not just a structure of matter and energy, but something that can be reflected upon, something that can be experienced, something that can inspire curiosity, even at its limits. And so, as we approach the very end of this journey, the need to go further begins to gently fade. not because there is nothing left to explore, but because we have reached a point where exploration becomes reflection, where understanding becomes quiet appreciation, and where the smallest possible scale leads not to a final answer, but to a deeper sense of wonder. In the final moments ahead, we will let that wonder settle completely into a calm, slow drift through the universe as a whole, not focusing on what lies beneath, but simply resting within what is. And now, we arrive at the quiet end of this journey, not with a conclusion, but with a gentle stillness. Because after traveling from the scale of your everyday world, down through atoms, into particles, through uncertainty, across the boundary of the Planck length, and into the unknown beneath it, there is nothing left to chase, only something to feel, a sense that the universe is deeper than it appears, and at the same time complete exactly as it is. If you imagine once more that smallest scale, that boundary where distance loses meaning, it no longer feels like a distant, unreachable place. It becomes something quietly present, not somewhere far away, but something that exists beneath everything, beneath every object, every moment, every thought. The Planck length is not just at the edge of reality. It is woven into it. It is present in the space between atoms, in the structure of spacetime, in the earliest moments of the universe, and in every interaction that has ever occurred. And yet it remains hidden, not because it is distant, but because it belongs to a level of reality that does not reveal itself directly. And there is something peaceful about that, because it reminds us that not everything needs to be seen to be real. Not everything needs to be fully understood to be meaningful. Some things exist quietly, shaping everything, without ever stepping into the light. And as you sit with that idea, the need to define it begins to soften. The questions that once felt urgent begin to slow. What lies beyond the Planck length? What space is made of? Whether time is continuous or discrete, they remain, but they no longer demand immediate answers. They become part of the background, like distant stars, always present, gently glowing, without asking to be resolved. And in their place, something else begins to take form. Quiet appreciation for the layers of reality, for the fact that something as vast as the universe can contain both clarity and mystery at the same time, that it can be understood in part and still remain endlessly deep. And perhaps, in a way, this is what makes it feel alive. Not alive in the biological sense, but alive in the sense that it is not fixed, not fully captured, and not reduced to a single explanation. Continues to reveal and to withhold in balance. And somewhere within that balance is where we exist, aware of the surface and aware of the depth beneath it, able to explore and also to rest, because in the end, this journey was never about reaching the smallest point. It was about seeing the universe differently, seeing that what feels solid is mostly space, that what feels continuous may be built from something discrete, that what feels fundamental may itself emerge from something deeper. and that even at the smallest possible scale, there is still mystery, still quiet, still something beyond. So now, as everything gently slows, you can let go of the descent, let go of the need to go further, and simply imagine the universe as a whole, vast, silent, stretching across unimaginable distances. Galaxies drifting slowly through space, stars forming, shining, fading, planets turning in quiet orbits, and beneath all of it, far beyond what can be seen, a boundary, a limit, a smallest scale that holds everything together without ever being directly touched. And as you rest with that image, there is nothing left to solve, only something to experience, a calm awareness that you are part of this universe, not separate from it, but within it, made from the same structures, shaped by the same laws, connected to the same hidden depth, and that even if the deepest layer remains out of reach, the fact that it exists is already enough, enough to inspire curiosity, enough to create wonder, enough to remind you that reality is far richer than it first appears. So as your thoughts begin to slow and the edges of this journey soften, you can simply drift, no longer moving downward, no longer searching, just floating quietly within a universe that is both knowable and unknowable at the same time. And if you are still here, still listening, still gently aware, let me know by typing the number 3 in the comments. And wherever you are in the world tonight, may your thoughts drift peacefully through space, through time, and into the quiet mystery that holds it all together.